again. So today we'll be talking about the energy module of the Year 11 chemistry syllabus. And our focus has been combustion reactions. And in the last lesson we looked at just how to identify reactions. So in today's lesson we'll actually look at combustion and what kind of reaction that is and how to generalize it and how to know if the reaction you're seeing is actually combustion or not. So here is one example of combustion. It's in a typical industrial plant. It could be that they're producing methane as a byproduct, and so often methane is just burnt in open air because they want to just get rid of it. This happens in a company this happens in plenty of companies, particularly the ones that are producing biogas. Sometimes they can produce more gas than they can actually use, so they need to get rid of it and burn it. Okay. So what is combustion as a reaction? So combustion reactions can be categorized as any exothermic. So exothermic meaning that it releases energy by heat transfer and light as well. So it releases a lot of energy and we feel that as heat, okay? And it happens between any fuel and oxidant. So a fuel could be some kind of hydrocarbon, could be coal, could be natural gas, could be something like magnesium even. And an oxidant. So that sounds like something like oxygen, but yeah, so it could be just oxygen. But there are other things like nitrates and other chemicals with oxygen in them that can also act as an oxidant. So this is just a general way of describing them. So these reactions release heat and light. And generally the fuels are some form of hydrocarbon and the oxidant is oxygen. So in general, we see hydrocarbon fuels and oxygen as the oxidant. And there's a furnace. Again, it looks fairly unimpressive, but it's very, very hot. It's been optimized probably to somewhere on the order of 1,000 degrees Celsius or higher. So it's obvious from the production of heat and light that this is a chemical change. So we talked about this last lesson, what a chemical change is and what a physical change is. And because the heat release is so big and there's also light as well as gas production, we can see that it's a chemical change. Additionally, the products are not easily separated. So carbon dioxide is usually a byproduct of combustion of fuels. When you look at it, if we could easily reverse carbon dioxide into something else, we probably would have done so a long time ago because there's a lot of concern about global warming and CO2. So, of course, if that was easy to do, we would have done it already. So a very common combustion system is the candle combustion system. You may not have ever thought about candles other than when it's a blackout, but they are quite an impressive or quite an interesting system to study when you're studying combustion. So candles have been studied for a long time, mainly because they're quite stable flames, and anyone has access to a candle, so you can study them if you're a sort of not the most well-funded scientist of all time. So these candles have been studied for a long time. So firstly, the candle wax itself, which is that red stuff at the bottom, goes through a number of physical changes before it starts reacting at all. Okay? Because something you should note about combustion is that none of the reactants are ever in any other phase but gas phase, and by phase I mean state. So if you want a combustion reaction to happen, you need gases only. You can't have anything else. A natural question to follow that is, well, what about wood? I can burn wood. So you just said that you need gas. Well, when you burn wood, you never see wood just light on fire straight away. You have to heat the wood first. And that heating of the wood breaks down in a decomposition reaction, the wood particles, and turns them into a gas, which seeps out of the cracks in the wood, and then that's what actually catches on fire. Okay, so just remember that you always need a gas, otherwise you won't be able to get a flame. So for this reaction, you have the solid wax. It melts, turns into liquid wax, which you can feel, you can see it, you can pour it out. And then it gets turned into a gas before it burns. Okay. So the candle wax will form a pool, which will be drawn up the wick. Okay, so here you can see there's a little sort of crevice or sort of bowl area down at the bottom of the wick. And so when the flame is there, the wick will sort of draw the liquid up that string, which is called the wick. And then the heat from the flame will actually vaporize the wax. And then you get it to burn. And so the flame is blue at the base and yellow-orange towards the center, which you've all seen. That implies that the bottom end is hotter than the top. And the mass of the candle will generally diminish as we continue combustion. Okay? So candles are a well-studied system. And here up the top, what you'll notice is that you'll see higher levels of soot because the combustion is less complete, because it hasn't had enough time to mix with the oxygen. Whereas at the bottom, or the oxygen has been consumed on its way in. And on the bottom, it's slightly more complete because there's slightly more oxygen available. Okay. So that wraps up today's lesson on combustion. So we've defined what combustion reactions are and how to sort of see them. And we've looked at a very simple system of the candle combustion system. Okay. So we'll move on to the question segment, and hopefully you'll be able to answer these questions, or at least you'll learn something new about combustion from these questions. Okay, so question 4. Combustion is any reaction between fuel and oxidant. So again, we're going to see that that kind of topic keep coming up. So write out chemical equations for the combustion of magnesium. Okay, so here's the first one. So we're just going to assume for now that oxygen is the oxidant, because that kind of makes sense, and magnesium is our fuel. Okay, so if you check your periodic table, magnesium has symbol Mg, and we'll say it's a solid for now. And then we have an oxygen. Okay, so we haven't put any of the numbers in yet because we haven't balanced it. So the question is, what is it likely to make? Okay, so it's probably going to be some kind of Mg plus O2 or O or something. So in order to figure that out, and maybe we'll put gas here. To figure that out, we need to know the valency of these guys. Okay, so if you look on your periodic table, Mg, or magnesium, is in group 2, which means that it has 2 valence electrons. And in order to attain stability, it needs 8 in its outermost shell. So what we can do is we can either grab 6 electrons from somewhere, or magnesium can just give away 2 electrons and then sort of cheat and go down a shell, if that makes sense. So if it gives away 2 electrons, then it's left with positive 2 charge, because each electron is negatively charged, but the proton number hasn't changed. So if you got rid of 2 negatives, you get 2 positives back. So it has the valence of 2 plus. Okay, my pluses are not that good. Now, oxygen, it's in group 6. So if you look, you can figure that out. And so oxygen needs either to get 2 electrons or give away 6. So if it's obviously easier to pick up 2 electrons. Now, if it picks up 2 electrons, it has 2 more negative charges, and there's no additional protons, so it becomes 2 minus. Okay? So for every 1 oxygen, you can see there's 2 minus, and for every 1 magnesium, there's 2 plus. So then it must mean that MgO is the final product, right? Now, the question becomes, how do we balance for the remaining part? So there are 1 oxygen on this side and 2 on this side. So we'll put a 2 here. So 2 oxygens, 2 oxygens. Now if there's 1 magnesium, there's 2 magnesiums here, sorry, but there's only 1 here. So we'll put a 2 here. Okay? And that balances our equation. Okay? And that's the final equation. And if we look at the answer, there it is. Okay? So moving on, methane. So methane's quite a bit more complex fuel. If you haven't seen it yet, that's okay, but you will cover it again in year 12. Methane is CH4, so 1 carbon, 4 hydrogens. Okay. We're going to say again that it's oxygen, but the thing that we're interested now is what is the products. Okay. So the products are always going to be CO2 and H2O. So when we burn anything, we always get CO2 and H2O if we have enough oxygen available. Okay? That's what we call complete combustion. If you got any other substances like CO or just plain C, then you would have incomplete combustion. And it meant that you didn't put enough oxygen into your system. Okay? But now we've got a balance. So let's start with carbon. So here's one carbon, here's one carbon. So it's balanced. Now what you want to do is you always want to balance the chemicals that appear only once on both sides. So what do I mean by that? You can see hydrogen appears only in this chemical methane on the left-hand side. Now hydrogen only appears on this water on the right-hand side. So that's your next best bet to sort of balance. So when we looked at carbon, we looked at there's one carbon on this side, and carbon only appears in the carbon dioxide on this side. But oxygen, however, appears here and here, and only appears once here. So oxygen will be quite hard to balance if you try to do it first or try to do it second. So whenever you see it appear more than once, you want to do that one last, okay? Because otherwise you'll get really confused and then you'll have to keep changing numbers and you might get a very messy final solution. Okay, so we have four hydrogens here and 2 hydrogens here. So to balance it, easy, just put a 2 here. So now we have 4, 4. Okay, easy enough. Now that we only have oxygens left to balance, we would balance the oxygens. So you got 2 times 1, so that's 2. 2 here as well. So in total we have 4 oxygens. Oops. That looks more like 40, doesn't it? Ox. Okay. And on this side we have 2. So the easy solution is just to put a 2 here. Now we have 4 on this side, 4 on that side, and we're all balanced up. Okay. And if we look at our final solution, it's no different. Okay? Simple. So moving on. Okay, so it's a bit tougher now. Assuming paraffin wax is given the equation C30H62, write a balanced chemical equation if only CO2 and H2O are products. So write a balanced equation for its combustion. Now, again, we're assuming that oxygen is our oxidant, so that's something that we need to be aware of. So we've got this C30H62 plus oxygen goes to form CO2 plus H2O. Okay? There you go. Now, okay, for the more mathematically minded, we won't need this so much now. For the more mathematically minded, I've put in A, B, and C. And they're just the coefficients, so they tell me how much to multiply by. Now, for the previous system, it was quite easy, right? We could sort of just break it up, look at it. But this one's quite a bit tougher. And so a more sort of rigorous way of doing it, I'll show you now, which never fails, okay? So let's see if we can do this. Okay, this is again quite not too bad a fuel. It's not too complex, but when we get to very, very complicated fuels, this process will never lead you astray. Okay, so we've got A, B, and C, and we need to just find out what these numbers are. Okay. So the first thing to do is balance for C, remembering that it appears only once on each side. So we'll start with that one. You could have started with H if you really wanted to, but I like to start with C. It's up to you. Personal preference stuff. Now, if you look at the number of carbons on the left-hand side, it's 30. And so the number of carbons on the right-hand side is B. Okay? And they have to be the same. So the number of carbons on this side has to be the same as the number of carbons on this side. So 30 has to equal B. So that tells you immediately that B is 30. Okay? Simple. Now, for balancing of hydrogen, because remembering that we want to balance now hydrogen because it appears once and once. So we have 62 on the left-hand side and C times 2 on the right-hand side, or 2C on the right-hand side. So for those and they have to be equal to one another. So 62 equals 2C. And for the math-minded people, you should easily see what the next number should be. C is 31. Okay? So 62 divided by 2 is 31. Okay? That's clear. Now we have oxygen left to balance for. Okay? Oxygen's the most complicated one because it appears twice. Now, so 2 times A, okay, that's how many oxygens are on the left-hand side. 2 times A, or A times 2, okay? Now on the right-hand side, you've got 2 times B, okay? And you've got C times 1, okay? So there's a 1 here, C times 1. So and they both have to equal each other. So 2B plus C has to equal 2A, right? And we already know what B and C are. We worked it out in the previous question, or previous parts of the question. So 2B is 60, so 2 times 30 is 60, and C is 31, okay? Which leads to A equals 91 on 2, okay? And then when you sub in all those numbers into the equation, that's the final equation, okay? So that's how you balance equations. This is a more rigorous way of doing it. Many people just kind of eyeball it. They just say, look, okay, I can see exactly what the answer is straight away. But if you can't see that all the time, this is a good way of doing it. Okay. So that wraps up today's lesson on combustion. So we looked at combustion systems for what a combustion system is, how it works, and what exactly is a candle combustion and how that works. And we looked at some questions on how to write up chemical equations for combustion. So in the next lesson, we'll do more on chemical reactions, and so I look forward to seeing you at our next lesson.